Okay, this is MCT4C day 23. The lesson is 3.5, solving problems involving vectors, the last lesson of the third unit. And our goal in the 3-minute review today is to solve problems involving the difference of two vectors. Essentially today is just more problems day, so we'll see a few examples and then set you off to solve some on your own. This one looks like it's a huge, big, long deal, but there's a point to be made. It says Ferd walked 2.4 kilometers east and Dreff walked 3 kilometers on a bearing of 300 degrees. So draw a diagram to represent the situation. I'm not going to worry about a scale diagram this time. So Ferd's walking east. Let's say that's 2.4 kilometers. That's 2.4 kilometers. And Dreff, I guess they started at the same spot, but it doesn't really say, walked on a bearing of 300 degrees. So remember, bearing's always from straight north, so it's over here somewhere, like this. And he walked for a little bit longer, 3 kilometers, where this angle is 60 degrees, right? Because all the way around is 360, bearing of 300, 300 minus 60 is or 360 minus 60 is 300, right? So this angle here is 60. And this is Dreff's walk, which is 3 kilometers. Great. There's the situation. So the question is, in B, so this is A, how far and at what direction would Ferd need to walk to meet Dreff? So Dreff's and this is called Dreff's displacement. So it's a vector quantity, right? So, well, Ferd's here, and he'd have to walk in this direction, and at that distance, that magnitude. So I'm going to change the color of that just so we can see it. I'm going to call that the displacement vector, okay? Now how are we going to find it? Well, notice that we've got the magnitude of this thing is what we'd like to find, and then the direction as well. This angle here, that's in between the two walk distances, 2.4 and 3, is 90 there, 60 there, it's 150. So this angle here, that's 150, right? And now I can use the cosine law. Can't use the sine law because there's no angle side pair, but we've had lots of practice at that. So 150, bing, 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 make sure you take the square root at the end, and you get about 5.2 kilometers. So he's got to walk 5.2 kilometers, and notice that's a little bit shorter than the two totals, right? Then retracing his steps and then retracing Dreff's steps. A little bit shorter because he's going off at an angle. And then now I can actually find that angle, right? And I'm going to report this angle, this direction, in whatever way I want, thinking of this as my direction crosshairs there. I'm going to use the sine law, why not? Over 3, because I got my angle side pair now, right? Cross multiply. Oops. So 350 over 5.2. Bing, bing, bing. Calculator action. Inverse sine at the end. 17 degrees. So if this angle here is 17 degrees, how would I describe it? Well, my direction, I could say it's on a bearing of 270 plus 17, right? So Ferd must walk 5.2 kilometers, and then a bearing is 270 plus 17, 200. 87 degrees. Or if I wanted to report it in the quadrant bearing, it would be north this many degrees west, which is, if this is 17, this is going to be 73 in there. So this would be also reported as north 73 degrees west, if you like. And this is B, part B. Explain your answer in B as the sum or difference of vectors. Well, I can see this answer certainly isn't this one plus this one, because if I added the two, this one would be sort of shooting up this way, and my displacement or my resultant vector would be going in that direction. So something weird's going on here. Let me see if I can clean up this diagram just a little bit so I can maybe look at it. To get this one to start here, that means this, the vectors have to start at this spot, right? Tails to tips. And so I should be thinking about the vector going this way, right? Which is actually the negative of Ferd's vector. So if this is Dreff's vector, darn, I'll call him E for Dreff. Ferd and Dreff, then I can see both on the diagram and using some vectors that I have the displacement vector is actually negative Ferd plus Dreff, or simply the difference between the two, isn't it? Clean this up because this looks messy over there. Is your answer in B the same as Ferd's displacement from Dreff? Ferd's displacement from Dreff would be, if here's Dreff here, here's Ferd here, would be the opposite direction. No, it's not the same. In fact, Ferd's displacement from Dreff would be basically the opposite vector. It's going to be F minus E, isn't it? It's the opposite direction. And these are the types of problems we're up against today. And we've been doing these this whole unit. We've got a whole bunch of them that we've already encountered, and maybe some new ones. Solve problems involving the sum and difference of vectors taken from real-life applications. The airspeed ones, where the airspeed is a certain amount, and then the wind speed is blowing the plane off track, and then on the ground, it's just the sum of the two, right? It's airspeed plus wind speed. And if we ever wanted to solve for one of these, we could just rearrange, right? If we wanted to find airspeed or we wanted to find the strength of the wind, we could just rearrange this little equation. Similarly, the total velocity of a boat in water, somebody's paddling away with velocity b, but then the current is blowing them off course, then we add those two vectors to get the total velocity. Displacement we just talked about, so object A moves along vector OA, and this time we've got and then along vector AB, so they go this way, then this way, while the total displacement is OB, right? OB equals OA plus AB. Now notice this is different than the 3-minute review question where we were talking about displacement of one object from another. This one is total displacement after the object moves on two parts of a walk or two parts of a journey. Similar to this displacement from the 3-minute review is the relative velocity question. If object A is moving with velocity A and object B is moving with velocity B, then the motion of B relative to A is, and this is R is the relative velocity, is B minus A, the velocity of somebody else with respect to you. So I've got an example for this, and you don't have this in your notes, but it'll illustrate why we subtract. All right, so we got a YouTube here somewhere. Where's my YouTube? There it is. And when we picture this, we're in the car driving at 100 kilometers, and the Ferrari that passes us is going 130. They're probably going more than that, but the trucks in the other lane are going 80. But just pay attention to the Ferrari for now. So notice they're going in the same direction. What's the relative velocity? So what's the velocity of the Ferrari with respect to us? Well, we're going in the same direction. It looks like if we were still, the Ferrari would be going away at 30 kilometers per hour, right? So it's going to be the velocity of the Ferrari with respect to us, right? But now if we were in the Ferrari, picture that, that'd be awesome, for one, if we were in the Ferrari. But what would it look like? It would look like the clunker is going backwards, right? So the velocity of the clunker subtract the velocity of the Ferrari. This would be the 100 subtract 130. Notice we can just subtract in this case because they're in the same direction. The direction sort of cancels each other out. And then I'd get a negative number, right? It looks like the car is going backwards in some direction. Now let's think of the truck. I don't even know if you noticed the truck. If we're in the clunker. Well, the velocity of the truck, well, it's going in the opposite direction at 80 kilometers, and we're going 100. Well, their relative velocity is 180 kilometers per hour in the opposite direction, right? Where the negative sign means the opposite direction. So that's why we subtract. Hopefully that makes sense. And there's lots of neat problems you can solve with respect to this. I'm going to check my time, and then we'll get on with the rest of the examples here. How much time? I'm going to stop there and pick it up in video 2.